So now that we know a little bit about titration and indicators and how they work, we can specifically talk about titration and calculations with titration. So one of the things you have to know when you're actually titrating is the equivalence point. This is basically the point of the reaction when the two substances are equivalent to each other. And this also means you are done titrating. So you're going to look for the slightest permanent color change. I know it barely looks pink and this has phenolphthalein in it, but that is a great endpoint. This is over titrated. Looks pretty, but over titrated. So basically what you do is you have your two substances separated, you put your indicator, in our case phenolphthalein, and you add and you swirl. And eventually you're going to start seeing a color change, but it doesn't stick. As you swirl, it disappears. Once you start getting the color to stick longer before disappearing, you want to slow down your addition from the burette into the flask. As soon as you see that barely there color change that sticks, you're done titrating. If you add too much, you get a darker color. Once again, you've over titrated. So this is also called the end point of titration. So depending on your substance, in this case, we have an acid, strong acid, and then we have a weak acid. You can see that the equivalence point changes when you have the addition of sodium hydroxide base. So it depends on the substances as to the actual equivalence point. So it's not going to be the same if the molarity of the acid or base has changed. And this is just a funny meme. Basically, it's your heart rate when you're titrating. Anyone that's titrated can relate to this. So everything's looking great. You have some color sticking. You swirl it, maybe one more drop, and then boom, you've over titrated and essentially ruined your titration. Okay, so a primary standard solution is the solution of the two that you're titrating in which you know the concentration with confidence. You have to know one of the two substances concentration. You're then going to use this substance's concentration and the titration experiment and the volume you've used to determine the unknown concentration of the other substance. So this leads us into titration calculations. For titration calculations, you're going to use this formula. Capital MA/VA equals capital MB/VB. So you're multiplying the molarity concentration of the acid by the volume of the acid in milliliters, and that should be equivalent to the molarity of the base concentration multiplied by the volume of base used. Once again, usually in milliliters. Now, if you have one substance in liters and one in milliliters, you do have to make sure they're still both in the same unit. So you would either have to change both liters or both to milliliters. If they're both in liters, which is uncommon, you can leave it like that. But if they're different, you need to convert them, and usually we use milliliters. So you're going to be given 3 out of the 4 variables, and you will solve for 4. So it's just simple algebraic rearranging and ultimately multiplication and division. So let's try an example. I find it helpful to actually highlight doing these ones. Okay, so once again, I like to make a list. You don't necessarily have to, but I need to know MA, molarity of the acid, volume of the acid, VA, and I need to know molarity of the base, volume of the base. I'll be given 3 of these, solving for 1. So in a titration, 27.4 milliliters of a 0.0145 molarity base, sodium hydroxide, the base, is added to a 20 milliliter sample of HCl, which is an acid, hydrochloric acid. What's the molarity of the acid solution? So I think it's helpful to highlight and actually make a list, but you don't have to. So I am solving for MA in this case. VA is 20 because it says 20 milliliters of a hydrochloric acid solution. MA was my molarity of my base. And then VB is the volume of base. So you just have to make sure you're putting these in the right spot. So my equation is MAVA equals MBVB. I am solving for MA, so I'm going to divide both sides by VA. And then I can just plug in MB, forget units, times VB, all divided by VA. So milliliter is going to cancel out milliliter. Oops, I forgot my unit. I'm left with molarity. So plug that into your calculator. I get my MA equals 0.021 molar. Best way to check your answer is plug back into this equation. MA times VA should be very, very, very close to MB times VB. If they're off by more than a couple decimals, you've done something wrong. Okay, let's try another. Before I even read the problem, I'm going to make my list. A 15.5 sample of a 0.215 molar KOH solution, that's a base, so these numbers go with my base, was required 21.2 milliliters of acid solution. Once again, calculate the molarity of the acid, specifically acetic acid, which is also commonly known as white vinegar. So once again, I don't know my molarity of acid, but I do know my volume of acid. And I know my molarity of my base. Now you can see why chapter 15 kind of intertwines with chapter 16. You have to know how to tell the difference between an acid and a base, given a chemical formula. Okay, so now I have a list using my titration calculation, equation, and once again solving for MA, divide both sides by VA. So molarity of my acid is going to equal my molarity of my base times the volume of base used divided by the volume of acid that was needed. So once again, you have to make sure you put these in the right spot. So go ahead and solve that out. I got that the molarity of the acid is equivalent to 0.157. And go 3 decimals since these are very small numbers. Okay, once again, if you plug everything back into this initial equation, you should get both sides very, very similar to each other. Okay, try another one. Okay, so reading the problem, 20 milliliters of a 0.01 molar aqueous acid solution, HCl hydrochloric acid, is required to neutralize a 0.00667 molar solution of sodium hydroxide, a base. What volume of base is needed? So now I'm solving for VB. So let me fill in what I know. I know the volume of acid, I know the molarity of acid, and I know the molarity of base. And I am finding volume of base. So dividing both sides by MB gives me volume of base. So molarity of my acid times volume of my acid. I put this backwards, I'm sorry. I put VA first. The volume of my acid times molarity of my acid divided by molarity of my base. Don't forget units. Okay, so I'm solving for VB, and I found that VB is equal to 29.99 milliliters. Or if you round up to 30, that's fine. So let's just try to check this. So what's 20 times 0.01? Let me get my calculator. Okay, sorry. 20 times 0.01 equals 0.2. So that's this side of my equation. Now let me take these two times each other. 0.00667 times 29.99. Those two equal also 0.02. Blah, blah, blah. That's this side. So that's what I'm saying. You can always check your answers and know if you're right or wrong. If you get too much of a difference besides a couple decimal places, something's gone wrong. All right, try this one by yourself. Pause the video, check your answers. So in this case, you're solving for molarity of, volume of acid. So you know the molarity of the acid and base, and you know volume of base. So in your equation, you should have Ma times B, reverse, MB times BB divided by MA. So that's done here. Plugging this into my calculator, I get volume of acid to be 11.98 milliliters, or you could round up to 12. Once again, if you multiply both sides together, they should be equal to each other. Okay, one more. By titration, a 0.06, I cannot speak today. By titration, a 0.0176 liter solution of aqueous 0.026 molar H2SO4, that's our acid, will neutralize a 0.0165 molar LiOH, lithium hydroxide basic solution. What volume of alkaline solution is present? So if you're not aware, which you should be, alkaline means base. So I know Ma is 0.026, Va is 0.0167 liters. I know Mb 0.0165 molarity. I do not know Vb. So if I leave it like this, my volume of base is going to be in liters. That's okay. Or if you want to change this to milliliters, you would multiply by 1,000. It doesn't matter which method to me, you should still get the same answer. It would just be in liters versus milliliters. Okay, so I'm going to do it in milliliters just because I like milliliters better. If you do it in liters, that's fine. Just be aware that your value is going to be different because of the conversion, but still the same, if that makes sense. Okay, so I'm solving for VB. I divide both sides by MB, and then I get molarity of my acid times my volume of acid, don't forget units, all divided by my molarity of my base. So go ahead and solve that. I'm finding mine in milliliters. If you find yours in liters, that's fine. So I get my volume of base to be 27.73 milliliters. Once again, if you multiply the MB and VB together, it will be very equivalent to the MA times VA. But remember, if you did want to do this in liters, if you didn't want to convert, then you only need to do that, like I said, if you have both volumes and they're not equivalent in unit, or if the directions tell you to have it in one unit or the other. But if it doesn't say that, you can use whichever unit you would like. So if you did this in liters, you would just get a smaller number. You would get 0.2773. Same thing, just in a different unit. Okay, so that is titration calculations. NAVA equals NBVB. You'll be given 3 of the 4, where NA is molarity of acid, MB is molarity of base, and then VAVB are the volumes of acid base, either both in milliliter or both in liter, unless the directions state which one.